In this video, I want to give an example of internal forces to a system. So the system that we're going to be considering is a person standing on a boat. Now, I wouldn't recommend that you do this on a small boat. It will make it very unstable. But just for illustrative purposes here, we're going to pretend that this person is standing on the boat and it's very stable. So the system that we're considering is going to be the boat and the person. This is making up our system here. And the boat is just freely floating on the water, so it's free to move. And what's going to happen is this person is going to start walking forward on the boat. So if the person's walking forward on the boat, their foot is going to be pushing on the boat, and the boat is going to be pushing on their foot. It's going to be a Newton's third law pair, and they're going to be equal and opposite magnitudes. So down here at the foot, I'm just going to draw a force vector. I'm putting it here at the foot because that's where the force would actually, the exchanging of the forces would actually take place, would be where your foot's pressing off the boat. So I'm going to draw this force vector forward. And this vector is actually the force of the boat on the person. So force of the boat on the person. If you think about it, when you walk, you're pressing backwards with your foot onto the ground or a hallway or a floor, wherever you're walking. So if you're walking down the hall, you're pressing backwards with your foot onto the floor, and then the floor is pressing on you. So the act of the floor pressing on you would be the forward vector. It would be the opposite push to you pressing on the floor. So I'm going to draw this vector here, and this is the force of the boat on the person, and we know then there's going to be an equal and opposite force of the force of the person on the boat. And I'm just drawing it down here so we can see it and see that it's a different vector than the one that I've drawn above. Again, both of these forces would be occurring on your foot and on the floor. So I'm just putting it down here so we can see it easily. And we're saying then that this is the force of the person on the boat. And the magnitudes of these forces are the same. So the force of the boat on the person magnitude is equal to the magnitude of the force of the person on the boat. And this is Newton's third law. So this is an action-reaction pair. So the person starts walking forward, and, well, what's going to happen? So they're going to start accelerating. And let's give these two objects, the person and the boat, let's give them some masses. Let's say that the mass of the person, let's give this person 70 kilogram mass, and let's say that the mass of the boat is half of that, so 35 kilograms. Now, if the forces that are acting on the person are the same as the force that is acting on the boat, so if those forces are the same, but the masses are different, well, what happens then? So the force of the boat on the person, this is going to be the boat acting on the person. Well, what is the person's mass? So the mass of the person is 70 kilograms, and then that's going to be multiplied by the acceleration of the person. And the same for the force of the person on the boat. Well, now we have something acting on the boat. We have the mass of the boat times the acceleration of the boat. Okay, and just looking at this mass relationship here, just comparing these two masses, if I know that the person is twice the mass of the boat, so in other words, this value here, this MP, is twice this M sub B, well then, if these two are equal magnitudes, then the accelerations have to be different because the masses are different. If the masses are different, then the accelerations have to be different accordingly to make these two be equal. So if these two are equal and the masses are different, then the accelerations have to be proportionally different as well. So if you have twice the mass, well, then you're going to accelerate at half the rate. If you have 1/2 of the mass, then you're going to accelerate 2 times more than the heavier object. Hopefully that makes sense. The mass of the person is greater, so it's going to accelerate less. The mass of the boat is less, so it's going to accelerate more. So even though these forces are the same, as this person starts to move forward and accelerate forward because of that forward force, so we'll draw this as the acceleration of the person, well then the acceleration of the boat is going to be double that. So the acceleration of the boat now we're saying is double the person because it weighs half as much. So it has to be double. So this is the acceleration of the boat. So the boat's going to be accelerating more than in the backwards direction than the person is accelerating in the forward direction. So one other thing we have to consider here, we have two different objects. Now there's something called the center of mass, and on a person it's kind of like in the middle of their torso. And it's the average really of all the masses around some center point. And then you find that center point, and then that's kind of like the average of all the masses. You'd say, well, that's kind of where the middle of all the mass is located. So the center of mass for this system, initially, we would say, well, the person's heavier than the boat. So it's not going to be halfway between either end of the boat. It's going to favor the person, and then it's going to be up a little ways. So if I would have to approximate it, I would say that this point, actually let's make this red. This red point right here, we're going to call the center of mass. So this is the center of mass. And again, that's just kind of a way of thinking about like where the center average is of all the different mass that you have. For a sphere like the Earth, it's very simple. It's the center of the Earth. Because why? Well, it's a spherical shape, so all around it you're equidistant from all the other masses that are around you. So the center of mass is, well, the center of the Earth. And the center of mass for a person, since most of your weight is in your torso, your center of mass is going to be somewhere in the middle of your torso. But so we're calling this the center of mass of these two objects because we're combining these two objects and treating them as one system. So, okay, so you have this center of mass that's right here. Well, the interesting thing, since the boat is going to be accelerating backwards at twice the rate of the person, what you'll find is that the system as a whole does not actually accelerate. So the boat's going to be accelerating, and the person's going to be accelerating, and they have this equal and opposite force that are causing that acceleration, but the actual system as a whole does not accelerate at all. So the center of mass actually stays at the exact same spot. It does not move. It's as if all the other averages of the masses around it can change and shift a little bit, but the center of mass will not move. So it stays at the same spot, but now the person is going to be in the front of the boat. They will have moved at 1/2 the acceleration that the boat moved. Remember, the boat is going to be moving faster than the person. So the center of mass, it doesn't move, and we can say therefore that the whole system has not accelerated at all. All the movement and the acceleration is inside the system, and it's always balanced out by Newton's third law of pairs. We're going to be exploring this fact further, and just to write it explicitly, here's what I can say. So we have this already written down, that this one vector for the boat is twice the length of the vector for acceleration for the person. because the mass of the person is double the mass of the boat. So what we can say then is, because we're just dealing with this system that's by itself, we haven't dealt with any outside external forces. For example, if someone came along and they pushed the boat, or if the wind came along and moved the boat, we're not dealing with anything like that. We've only been dealing with just this isolated system. So there are no external forces on the system. And because of that, the system's center of mass didn't change, even though inside the system itself, there were things that were happening. There was motion that was occurring. Despite that, the center of mass did not change. So what we can say is that the sum of the forces on the system are zero. There are no net external forces that are acting on the system. Forces like a hand or the wind blowing on the boat or anything like that. So because the forces on the system are zero, then the acceleration of the system has to also be zero. So in effect, the system does not move. The system does not accelerate at all, despite these different types of motion that are occurring within the system. So we're going to be using Newton's third law of pairs to solve different problems, because we'll sometimes have different equations that are describing the individual components of objects that are a part of the system, but they'll be somehow linked together. They might share some force that is acting on both of them at the same time. Say, for example, a tension force that is on a rope that's holding two objects together. Something like that. We use those sorts of connections, and we use Newton's third law to help us solve different problems.